In lesson 6, we're going to look at some different types of special products or some unique products. Um, and this is really the last lesson on factoring, and then we're going to look at some unfactorable expressions and how do we actually divide polynomials. So for this lesson, we're focusing on a couple different types of situations. And the first one you've heard of before is difference of two perfect squares. So basically what happens is if you recognize something or an expression as a difference, meaning subtraction between two perfect squares, it's always going to be the case where the format of your factored expression will be an a plus b times an a minus b, given the fact that a has been squared and b has been squared and there's a difference between them. So essentially what you're doing is you're taking the square root of the first term, square root of the second term, and your signs will always be plus or minus when you go to factor. So let's look at this first one. So this first one is a difference of two perfect squares, because if you look, there's two terms. There's a minus between them, and each term is a perfect square. So essentially what you're going to do is you're going to have your two sets of parentheses, and you almost think of this as like square rooting each piece. So you square root 16x squared, you're going to get 4x. You square root 25, you're going to get 5. And it's always going to be plus or minus plus, doesn't matter the order of that between them, because you don't have that middle term anymore. So if you think of this in comparison to a quadratic, what this really is 16x squared plus 0x minus 25. So in order to add to 0, you have to have a positive and a minus, so that when you combine those terms, they undo each other, they cancel each other out. So that's why difference of perfect squares are always opposite signs, because of that middle term actually being 0x, and you're trying to add to 0. So let's look at some more. So this one here, again, we have a difference of perfect squares because we have two terms. Difference of perfect squares always has to be two terms. So we're going to have two sets of parentheses. We're going to square root each piece. So 36a squared is going to be 6a. 6a. Square root of 1 is just going to be 1, and it's going to be plus or minus for our signs. And again, the middle terms will cancel because we have a positive and we have a negative. We'll multiply our last terms to get that -1. So that's again why the signs are opposite, because we're going to be multiplying to get a negative. But that's why it has to be difference of perfect squares, is because you're always going to be multiplying opposite signs, and that means they'll have to be negative. Also keep in mind when you're doing difference of perfect squares is if there's a GCF, you always want to take care of that first. In these examples, we don't have a GCF, but if there were a GCF, I would have factored that out first and then applied difference of perfect squares if it works. Otherwise, the quadratic factoring, you really have to like just recognize what pieces or how, like what type of factoring is going to be used. So whenever it's two terms, check for difference of perfect squares. So now this one is actually going to be a difference of perfect squares, even though you might not think so right at first. But because it's x to the fourth and y to the fourth, I can take the square root of those. The square root of x to the fourth is actually x squared. Because what this really means, the square root of x to the fourth, really means what do you have to multiply by itself to get x to the fourth? Well, the answer to that is x squared, because when you multiply variables, you add the exponents. So I would do x raised to the 2 plus 2, because you'd be adding the exponents, which would give me x to the fourth. So the variable that has to be multiplied by itself to get x to the fourth is actually x squared, which is why when you take the square root, you get x to the second. So bottom line here is whenever you're taking the square root of an exponent, it's really asking you what do you have to multiply by 2 to get that expression. So you can kind of just think of it as divide the exponent by 2. because if you're multiplying some, or if you're raising something to the second power, it's really multiplying the exponent by 2. So square rooting is really undoing that raising to the power of 2. So you're just dividing the exponent by 2. So over here, this is actually a difference of perfect squares because these are even exponents, they're divisible by 2. So now I can do my two sets of parentheses. I can square root each piece. Square root of x to the fourth is x squared. Square root of y to the fourth is going to be y squared because you have to multiply y squared by itself to get y to the fourth. And then you're going to have your opposite signs. And now if you look, we have another difference of perfect squares because I have two squared terms with a minus. This first term, though, is just going to stay x squared plus y squared because it's not a difference. Yes, they're both perfect squares, but it's not a difference of perfect squares. So there's no way for me to rewrite that where there won't be in a middle term so that there's a positive sign. So it just can't happen. It's not possible. So I'm going to just leave that one and then worry about this next piece. So the next piece is going to be x and x when you take the square root, y and y when you take the square root of y squared, and then you have your two separate cases. So that's it for that one. Just make sure you remember to keep factoring further if needed. This example here is kind of an unusual one, but it is actually a difference of perfect squares because this whole thing has been squared, which means if I take the square root of it, if you take the square root of x minus 3 squared, you're just going to get x minus 3 because it's asking you what have you multiplied by itself to get x minus 3 squared. Well, if you multiply x minus 3 times x minus 3, you'll get x minus 3 squared. So the answer is when you take the square root of something that's been squared, the square root and the squared term kind of just cancel each other out, they undo each other. So you're left with x minus 3, which really means, yes, this is a difference of perfect squares because you have this entire squared term and another square perfect square, and it's a minus between them. So what happens when you go to do this is the same exact thing where you take the square root of each piece. So we have x minus 3. And then we're going to have plus minus. We take the square root of 25. So we get 5. So then now if you look, you can actually combine some like terms here. So I can reduce these numbers. So minus 3 plus 5 is going to give me plus 2. Minus 3 minus 5 is going to give me minus 8. So there are my terms. Now, if you didn't recognize that as a difference of perfect squares, worst case scenario, you end up multiplying x minus 3 times x minus 3, simplifying, and then factor with what you're left with. So you could do that. It would take you a lot longer. So that's kind of, this whole lesson is really focusing on what are some shortcuts, like recognizing some of these special patterns. You can take some shortcuts. So the next type of pattern are perfect square trinomials. So meaning that we're multiplying something by itself, which is what we just looked at when we had that x minus 3 squared. If you were to actually multiply x minus 3 times x minus 3, you would get what we're calling a perfect square trinomial, which means that a and b have been squared. So if it's x plus b quantity squared, really what that means is a is squared, b is squared, and the middle term is always 2 times a times b. If it's an a minus b quantity squared, again, you're going to have a squared and b squared, but because of that minus, the middle term will be minus 2 times a times b. So basically, when we looked at this in the past, when we looked at multiplying polynomials, we were given this side, and we knew that we could square a, we could square b, and then we would multiply 2 times a times b. Now we're looking at undoing that process. So this time you're going to be given this side here, and you're going to have to go backwards. So basically, what you're looking for are the a values, so this term here and this term, you really want to look at, do you have perfect squares as the first term and the last term? And as long as you do, then all you need to do is just check to make sure that the middle term has been 2 times the square root of both of those outside terms, so the first and the last term. And it can be the minus times 2 times the square root of a and b. So that's possible, which just means then you would be factoring to this, a minus b quantity squared. So if you look at this first example, that's really this situation here where I look at the trinomial part of it, and I notice that I have a perfect square as the first term and a perfect square as the last term. So I know that this is a perfect square trinomial as long as this middle term is 2 times the square root, or negative 2, I should say, times the square root of this first term and the last term. So let me just take the square root of this first term. If I take the square root of the first term, I get 5x. And if I take the square root of the last term, I get 6. So basically, I know that this has to be a perfect square trinomial if negative 2 times 5x times 6 is equal to negative 60x. And if you check it, negative 2 times 5 is negative 10, times 6 is negative 60, and I have the x. So as long as when I take the square root of the first term and the last term, multiply them by either positive 2 or negative 2, depending on whatever that sign is, as long as that equals the middle term, then I know that these are perfect square trinomials, which means that instead of factoring them by multiplying by 25 and doing the factor by grouping, the shortcut here is to know that my answer just has to be, or my factors for this just have to be the square root of the first term, so 5x. It's going to be a minus because I had a minus 60, and the square root of the last term, which is 6. And again, you can't just assume, though, because the first and the last term are perfect squares, that it works. You have to check that middle term. So make sure that middle term really is 2 times the square root of each of those. So let's look at some other examples. So I look at this one here. Again, if you notice that you have perfect squares in the front and in the back, then this will be a perfect square trinomial as long as this middle term here is 2 times, or negative 2 times, the square root of the front and the last term. So if you take the square root, so in this case it's going to be positive because it's a positive 40ab. So it's going to be 2 times the square root of each of those. Let's make sure. So square root 16a squared, we get 4a. Square root 25b squared, we get 5b. And if you multiply these, you get 4 times 5 is 10, or 20, times 2 is going to give me 40. So 40 times ab works. So that means it works out. So that means this has to be a perfect square trinomial. So I square root the first piece, I get 4a. It's going to be plus between the terms. Square root the last piece, we get 5b. So again, it's just a shortcut. If you don't recognize the pattern, it's not the end of the world. You could figure it out another way. Keep in mind with these that you're always looking for GCFs first, which kind of brings us to this next example here. When you first look at this, this is not a perfect square trinomial. I don't have a perfect square in the front or in the back, but I do have a GCF of 5. If I factor out that GCF, then what happens is I end up with a perfect square in the front and a perfect square as the last term. X squared is a perfect square, 9 is a perfect square. So if I check this middle term, it should be 2 times the square root of each of those, which it is, if I square root each term. So that means I can rewrite this as a perfect square trinomial. Square root x squared, we get x. Square root 9, we get 3, and that's it. So again, just another pattern or another shortcut. One last special type of factoring. I'm not sure that you've seen this before, but it's called the sum or difference of two cubes. So we have the difference of perfect squares, but we also have the difference of perfect cubes in addition to the sum of perfect cubes. So for perfect cubes, there's actually these two formulas, and you can do it for sum or for difference. Where perfect squares, it's only factorable if it's a difference. But for perfect cubes, you could do it for sum or for difference. So here's your two formulas. And these formulas are probably new, so you are going to need to know them. And when I do them, I don't really like memorize the formula. I just kind of talk through the process as I factor. So what I really am doing is the first stage, if you look at this first formula here, it's a to the third plus b to the third. The first stage is just to take the cube root of each piece, and then you multiply it by the first term squared, which is the a squared, switch the sign, multiply the two numbers, a and b, and then square the last term. That's just how you remember it. So if you look at this first term, it's x to the third minus 8. Well, 8 is a perfect cube. 2 to the third is 8, and x to the third is a perfect cube. So what we're going to do is first we're going to have two terms. So the first two terms are just taking the cube root of each of these. So if I take the cube root, which means what times what times what gives me this number. So when you take the cube root of x to the third, you get x. Take the cube root of 8, you get 2. And you're going to keep the sign because it's a minus. And now from here, I'm just focusing on this term here. So I'm going to square the first, which is x squared. Then I'm going to switch the sign to plus. I'm going to multiply these two numbers, so it's going to be 2x. And then I'm going to square the b value or the number. So in this case, 4 when I square 2. So 2 squared. And it's always going to be positive for that last term. So the only sign that's going to be different here are these two signs have to switch. They're always going to be opposites. Oops. So that would be it. If you can factor this part here further, then you would. If you can't, then you just leave it as is. So this is going to be it for this one. So let's do some more just so you become familiar with it. Next one here we have, again, sum of perfect cubes, because 64 is a perfect cube, so is t to the third. So first thing I'm going to do is one set of parentheses, and I'm going to cube root each piece. The cube root of 64 is 4, because 4 to the third is 64. T to the third, if I take the cube root, I'm just going to get t. So I do my first set of parentheses is just going to be the cube root of each of those. The second set of parentheses is now looking at the first set here. So I'm going to square the first term. I'm going to switch the sign. So it's going to become minus now instead of plus. I'm going to multiply these. So it's going to be 4t. And then I'm going to add the last term squared. And that's going to be it. So again, I'm kind of like, this is how I do the problems, is I kind of just like walk through the process instead of memorizing the formula. So feel free though, you can memorize the formula and then just plug in, or you can just kind of talk yourself through the pattern that really is the formula. Let's do just two more. So here now we have some numbers in with each variable. Again, as long as the numbers are perfect cubes and the variables are perfect cubes, you can still apply the sum or difference of perfect cubes. So 27 is a perfect cube, so is 125. So it's two terms to start. It's going to be a plus between them. And I'm taking the cube root. Cube root of 27 is 3. And then I take the cube root of x to the third. Cube root of 125 is 5. 5 to the third is 125. And it's going to be y. And now again, now I'm only focusing on this piece here. Square the first piece is always the first part of the formula. Squaring the first piece means squaring the 3 and the x, the entire first piece. So it's going to be 9 because you're doing 3 squared, x squared. You switch the sign. You multiply the 2. So 3 times 5 is 15. X times y is just going to be xy. And then it's always addition at the end. Square the last piece. So we have 25 because you're doing 5 squared times y squared. And that's it. And one last example is an x to the 6 minus y to the 6. So it's kind of similar to that whole square root problem that we had when we take the square root of an even exponent. It's a perfect square because it's divisible by 2. When you want to take the cube root, it just basically means that your exponents have to be divisible by 3 because that means I can raise it to the third power. So it's what can I raise to the third power um, to get to itself, or what can I multiply by itself 3 times to get to this. So I can apply the difference of perfect cubes here. So what I'm going to do is I'm going to have one set of parentheses. When I take the cube root of this, it's going to end up being, so if you divide everything by 3, it's going to end up being x squared. So we're going to have, when we take the cube root, so we'll have x squared minus y squared. Because remember that the cube root of x to the 6 is going to be x to the second, because it's asking you what times what times what is going to give me x to the 6. And the answer is x squared times x squared is going to get me x to the 6. So it's a difference of perfect cubes. So first piece is x squared minus y squared. Now we're going to just focus on the two terms. So we're going to square the first term, which is going to be x to the 4th. Switch the sign, multiply the two, so x squared, y squared. And then the last term is going to be y to the 4th. And then from there, you just have to make sure that all of these are reduced. So I can actually reduce this piece here because it's now a difference of perfect squares. So now I can do x minus y, x plus y as a difference of perfect squares. I square root each piece, opposite signs, and then I can just carry this whole piece down. And then that'll be it.